Hello everyone, welcome to the next lecture in the course Remote Sensing Principles and Applications. In this lecture, we are going to see few properties concerning electromagnetic radiation. In the last class, we have seen the basic laws which helps us to calculate the amount of radiation emitted by natural objects. So, we know how electromagnetic radiation is produced in nature, the basic principles of it. So, now we are going to study what are the basic properties of this EMR and how these properties will be helpful for us in remote sensing purposes. The first property of EMR that we are going to study is known as the polarization. When I introduced you to electromagnetic radiation, we came to know that EMR consists of two components, electric field and magnetic field. We also studied these fields, two fields will be perpendicular to each other and also to the direction of motion. But even if we consider these two components are perpendicular to each other, in a 3-dimensional space they can take any orientation. They can be vertical, like electric field can be vertical, can be horizontal, or can be continuously changing its orientation and so on. So, polarization indicates the orientation of the electric field in electromagnetic radiation. So, in which direction electric field is oriented in relation to magnetic field and also in relation to the direction of motion. So, this is polarization. So, the sunlight that which is the primary source of energy for remote sensing purposes consists of waves at different wavelengths and with different polarizations, that is it is a mixture of waves which consist of different wavelengths and different polarizations. So, we naturally call the sunlight as randomly polarized, or some literature call it as unpolarized, that is it contains waves with variation in polarization. So, some of the common polarization are, we call it as like horizontal, vertical, circular and so on. So, first we see what a polarization is by two examples, then we will see more about few intricate details about polarization. So, in these two figures we have examples for two kinds of polarization. In the figure 1, like I label this as figure 1, this is figure 2. In figure 1, the red line is the electric field, blue line is the magnetic field. If we observe, the wave is progressing from left to right in the screen and the electric field is vibrating in a plane perpendicular direction of motion, and if we look at it we can see that the electric field is vibrating in a vertical plane, that is, say if we take this direction as x, this direction as y and this direction as z, then the wave is progressing in x direction, along the x direction, electric field is vibrating along the y direction and magnetic field is vibrating along the z direction. This remains constant throughout the wave progression. Look at figure 2. Using the same coordinate axis system, the wave is still progressing in the x direction. Here electric field and magnetic field are vibrating in the yz plane, that is perpendicular to the x direction, that is ok, but the orientation within the yz plane keeps on varying, it is not a constant. As the wave progresses, the orientation of electric and magnetic fields keep on varying, that is if an observer is standing here and viewing the say this is like eye of an observer, if the observer is standing here looking at the wave coming towards the observer, he or she can sense that the wave is now rotating, like the orientation is continuously rotating when it is coming towards the observer. So, the electric and magnetic fields are vibrating in yz plane only, but the orientation is not constant, it is keep on changing while coming towards the observer, and the observer can sense it is almost like a circle, like it is rotating in form of a circle. So, this is this kind of, in figure 1 the polarization in which electric field is vibrating in only one particular plane, we call it as plane polarized wave, that is the wave is vibrating or the electric field is oriented in only one particular plane, we call it as plane polarized wave. whereas in figure 2 we call this as a circularly polarized wave or circular polarization, whatever. Circularly polarized wave. So, essentially if the orientation remains in only one plane, we call it as plane polarized. If the orientation keeps on changing as the wave progresses, we call it like either if it is circle, we call it as circularly polarized, if it is elliptical, we call it as elliptical polarized. There are different names. So, how to relate this polarization with respect to the plane of incidence? That is, let us assume there is a plane or surface here, electromagnetic radiation is coming towards it and going to fall on it. Say this is the plane of incidence. Let us assume this is a plane polarized wave. If this particular incoming wave has its electric field oriented along this direction, that is it is vibrating, say if you take this as x, if this as y, if the electric field is continuously orienting itself only in the y plane, then this is like a plane polarized wave, and this direction of orientation of electric field is parallel to the plane of incidence. The plane of incidence is like this horizontal and the electric field is also vibrating parallel to it. Such orientation in which the orientation of electric field is vibrating in a plane parallel to the plane of incidence, we call it horizontal polarization. On the other hand, if the surface is like this is the incoming wave. In the incoming wave, the electric field is, if it is like vibrating in this particular direction, that is perpendicular to the plane of incidence, then we call that particular polarization as vertical polarization. So, if the plane of vibration is parallel to plane of incidence, that is horizontal polarization. If the plane of vibration is perpendicular to the plane of incidence, that is vertical polarization. And these two kind of polarization in which the electric field will be vibrating in only in one particular wave, such waves we call it as a plane polarized waves. So, some of the common polarizations we use are horizontal, vertical, circular, elliptical and so on. So, this is the basic orientation of electric field which defines with which polarization electromagnetic radiation is coming in. What is the need for studying polarization? Why we should care about in which direction the electric field is oriented? Isn't it necessary if we just look at the total amount of radiation coming in? Actually, the total amount of energy coming in or reflecting out of an object will vary with polarization also. That is, I will give you like an example. In this particular figure, same area is photographed at the same time, but with two cameras, one attached with a horizontally polarized filter and one attached with a vertically polarized filter. Okay. So, one on the left is photograph taken with the filter allows only vertically polarized light, and on the right the filter will allow only horizontally polarized light. So, you can see the picture is for the same region taken at the same time, but these two pictures appear completely different, because as we have studied that the incoming energy or the reflected energy, whatever may be, will have spectral variation, that we know, that is the energy will vary with wavelength, and also within a given wavelength the amount of energy will vary with polarization also. That is, say whatever energy coming in from the sun, a certain fraction of energy will be waves will be having certain polarization, some may be horizontal, some may be vertical, some may be like circularly polarized and so on. Similarly, when electromagnetic radiation is incident of an object and interacts with the object, naturally the polarization will change. Like some objects will reflect more of vertically polarized light, some objects will reflect more of horizontally polarized light and so on. So, essentially the amount of energy that is incident on an object and reflected on an object will vary with respect to polarization also. So, the sensor which we use should be able to capture this polarization effect. That is, by looking at the polarization also, we will be able to understand more details about the object. Okay, this object is reflecting more of horizontally polarized light. This object is reflecting more of vertically polarized light. So, such polarization information will help us to know more about the object, and limiting one particular polarization will actually limit the total amount of energy coming in. That is, like in this photograph itself shown in the slide, the one on the left actually removed all the horizontally polarized light. So, from the total amount of radiation coming in towards the camera, a certain amount of energy is removed, only vertically polarized light is allowed in. Whereas on the right side, only horizontally polarized light is allowed, vertically polarized light is totally removed. So, if you look at these photographs and infer, the one with vertically polarized light appears much brighter, the one with horizontally polarized light appears much darker. So, what it means in this particular scenario, when we look at the total amount of energy coming in, the energy had relatively a larger component of light that is vertically polarized rather than horizontally polarized light. So, by limiting the waves in certain polarization, we will be limiting the total amount of energy reaching an object. That is a major implication, and also as the objects interact with EMR, the orientation of electric field, that is the polarization, tends to change, which gives us an indication about the nature of the object. Normally, like when we go out in bright sunny days, we used to wear polarizing sunglasses. If we wear such polarizing sunglasses, the outer surfaces will not appear so bright, we will feel comfortable. Why? Because the polarizing sunglasses naturally filters out certain polarization out. Like some of the polarization will be removed. That means you are limiting the total amount of energy reaching our eyes. That is why our eyes appear comfortable when we wear a polarizing sunglass. So, polarization, having certain polarization filters will help us to limit the total amount of energy coming into a sensor. Similarly, based on polarization, we will be able to know more about the objects that is reflecting it, and this is really important when we do microwave remote sensing. In microwave remote sensing, the sensors will be capable of observing microwave signals in different polarizations, like horizontally polarized, vertically polarized, cross polarized and so on, and each object will behave differently under different polarized signals. So, polarization is really critical in order to understand about the nature of objects. The next property we are going to see about electromagnetic radiation is known as coherency. Before looking at what coherency is, let us quickly go back to our school physics days and recall what is known as a phase of a wave. So, we will see what is a phase of a wave. So, this is like one full cycle of a wave. Let us say a time is taken between like 0 and at certain interval time t, and at a certain distance d, that is lambda, it completes one full cycle. So, for this one full cycle of wave, at each stage we will be able to tell, we should be able to tell at which stage the wave is. That is, if I tell you, okay, this is like total time t naught, okay. If I say what is the stage of the wave at time t1, what is the stage of the wave at time t2, what is the stage of the wave at time t3. If I want to tell at which stage the wave is progressing at a given time interval, at which stage of wave is progressing, we have assigned certain angular values to it. Say for example, if the wave is just going to start from its 0th state, we call it as phase 0. Let us say after time period of t1, the wave has come to its peak in its positive side, we call it as phase pi by 2. Then after crossing the peak in positive side, it comes towards the 0 again, we call it phase phi. Then it goes in the negative direction, reaches a negative maxima, we call it phase 3 pi by 2, then again it comes back to 0. We call it phase 2 pi, then we say the wave has completed one full cycle. So, just for our convenience we say okay, the wave is, when the wave is progressing, at which stage the wave is, whether it is like in phase 0, phase pi by 2, phase pi, phase 3 pi by 2 and so on. So, the phase is essentially will tell us at a given time or at a given point in space what is the stage at which the wave has progressed. This is like a simple explanation for phase. We generally correspond angular values to it, and also commonly we call it as phase angle or phase and so on. So, two waves are said to be coherent when they have a systematic phase relationship between them. What is meant by a systematic phase relationship? Say two waves A and B are travelling together. If these two waves have same phase at a given time t or at a given space x, y, whatever, phase can be calculated both at temporal scale and spatial scales. So, if the phase is constant, if they have both the same phase, or if they have a same phase difference, then those two waves are said to be coherent. So, we will see this with few examples. There is two waves given here, one with like a blue color, marked with blue color, one marked with a red color. So, here what is happening is, say this is like the time axis. So, these two waves, like the wave is starting here, say I just extrapolated, and this wave is starting here. Say at a given same time interval, say at this particular time interval t1, the wave marked in blue is just starting here, whereas the wave marked in red is has started from a 0 value and is moving towards its peak. So, when wave 2, the wave marked in red color reaches its peak, wave 1 is still not reached its peak value. So, this denotes wave 1 and wave 2. So, I call this as wave 1, I call this as wave 2. Wave 1 and wave 2 has a phase difference among them. These two waves do not have the same phase, they have phase difference among them. So, if they have a common phase difference, if the phase difference remains constant throughout whenever it is along in the time axis, say if the phase difference is constant throughout as it moves the time axis, then we call this wave as coherent, that is the phase difference is there, but still the phase difference is constant throughout. We look at the example given in the bottom figure. Two waves are there, same blue wave and red wave, but here in this case both the waves are exactly in the same phase at the same time interval, that is when it is time 0 both the waves are starting. When the time is 2 seconds, it is like 2 units, both the waves are reached its peak in its positive side. When time is 4 both the waves are reached 0 again. So, essentially it means both the waves are exactly in phase. Then also we call these two particular waves as coherent. So, as long as two waves have same phase or constant phase difference, we call those waves as coherent waves. On the other hand, if the phase difference varies either with respect to time or with respect to space, then those two waves will not be coherent. So, those two waves should definitely maintain a systematic phase relationship. They should either be in same phase or have a constant phase difference. Then only we call those two waves are coherent waves. So, we go back to the previous slide. Yes, two waves will be perfectly coherent only if they are monochromatic and they are parallel to each other. So, what exactly monochromatic is? Let us say two example of two waves A, B. Okay, so, wave A is like this, slightly longer wavelength. Wave B is like this. Okay, so, this is some time t naught. In time t naught, wave A completes only one cycle, whereas in the same time t naught, wave B completes 3 cycles, which essentially means at any given time interval, say T1, T2 and all, if you calculate the phase between these two waves, the phase will not match, there will be a phase difference, and this phase difference will not be constant, the phase difference will be keep on varying as the time progresses. Because of this difference in wavelength and or frequency of these two waves, the phase difference also will be keep varying. So, unless these waves are monochromatic, that is they travel with same wavelength or frequency, they cannot be perfectly coherent. This is one thing. And second thing is the wavelength should be collimated. So, what exactly collimated is? They should travel parallel to each other, or they should be having same path length. Let us say this is point A, this is point B. Okay. So, one wave, like two waves are actually starting from point A with a wavelength lambda, and one wave is travelling directly to point B. Another wave is travelling in a different direction, there is a mirror kept here at point C. Another wave first travels towards C, gets reflected at C and then reaches A, let us assume. So, even though the net displacement of the wave is from A to B, because of the difference in length travelled and the difference in the time taken to reach A to B, these two waves, even if they were coherent at the initial starting point, due to the variation in the path length and the time interval t, they would have definitely become out of phase. Their phase difference or the phase relationship between them would have changed. So, two waves will be perfectly coherent only if they are parallel, that is they are travelling parallel to each other, and only if they are monochromatic. So, what is the implication of waves being coherent or not? So, another example is given in this particular slide. In this particular slide, we have seen these two waves are in phase, they are coherent. So, at a given time interval, they are having exactly same they are having certain phase, certain amplitude, like this peak or this trough we call it as amplitude. How much it is varying from the central 0 axis, 0 plane of vibration. So, when two waves are exactly in phase, the amplitudes will add up and will produce a net resultant wave with an increased amplitude, like these two amplitudes will add up. Say if this is 2 unit, if this is 2 unit, when they add up they become 4 unit. Similarly, on the negative side also, this is -2, this is -2, this becomes -4. So, when two coherent waves meet up, they produce what is known as interference, that is their amplitude changes because of the mixing of or the interference of these two waves. So, if two waves are in phase with each other, the amplitudes will add up and it will produce a net resultant wave with a much larger amplitude variation. On the other hand, if two waves are coherent, but they are not in phase, like here wave 1 and wave 2, they are coherent actually, they have a constant phase difference between them, like it is the phase difference here, it is pi by 2 on the positive side, here it is 3 pi by 2 phase. So, the phase difference is more or less constant, here when it reaches 3 pi by 2, here it is pi by 2. So, the phase difference is constant. So, these two waves are coherent, but when they mix together with each other, because of the exact opposite sign in amplitude, they get nullified and produce a wave with 0 amplitude. That is, when two coherent waves meet, they either increase the amplitude of the net resultant wave or they decrease the amplitude of the net resultant wave. This is what we call it as interference. So, coherence, sometimes it will be like positive to us, sometimes it will be negative. Like if you look remote sensing images, due to coherence there can be some bright patches all along the image which will like obscure our signals. It is essentially it will occur more in microwave remote sensing, the coherence is quite a lot. So, coherence or interference will kind of act as a minor disturbance for us in remote sensing images. So, this is one of the important property about EMR that we should keep in mind. Coherent radiation produce interference. The interference can be positive interference, that is the amplitudes can add up if two waves are in phase, or the interference can be negative, that is those two waves can cancel out each other if they are out of phase. But non-coherent waves cannot produce interference, like if the waves are not coherent, interference problem will not be there. Okay. So, just to summarize what we have learnt in today's class, we have studied two important properties of EMR. One is polarization, another thing is coherence. So, polarization will help us to know what is the amount of, that is will help us to understand okay, what much of energy is coming in with different polarization and also how the objects interact. And second, we have seen what coherence is and how coherent radiation will either increase the amplitude of the net resultant wave or decrease the amplitude of net resultant wave. So, with this we stop this particular lecture. Thank you very much.